All right, so here's the solutions portion to this. And in this case, we're using the solubility rules that we had above. You have those little pink cards of this, but you also have this on the back of your periodic table in the form of a chart where you can match up the ions that are a part of it. But if we go all the way up to the front page of the FERP, this is you can see those are our solubility rules there. So using those, it tells you what's soluble or insoluble, and that helps you out here. So these in order, insoluble, which means it is a solid. It means that it does not dissolve. And then we have soluble for the next one, which is aqueous. We have soluble here as well. Those both have, one's a nitrate, and they both have the alkali metals in them. So this is going to be aqueous as well. It dissolves. And then potassium or calcium carbonate is insoluble, which means it is a solid. And we again call a solid a precipitate in chemistry. And that's just based off of since it's not able to stay dissolved, and you see it form when you get two substances to react. That's what we end up using to confirm that a reaction has occurred, that solid insoluble product or precipitate was formed. So as we're looking here, again, 100 grams of water is also the same as saying 100 milliliters of water. And with these problems, all of these amounts on this left side right here, so all of these values are how much of that particular substance we're able to dissolve, right? And it's in 100 grams of water. And I'm sorry, please don't mind the dogs doing their dog things. But that's how much. So the 100 grams of water is kind of just known. So we state it, but it's something that you can kind of, if you want and if it helps, just ignore effectively. Unless that number is something other than 100, then you can just ignore that. And so really what we're doing is we're just kind of using the temperature down here and the grams of potential solute that we could have to answer all of these, ignoring that other tidbit about the water. So at 40 degrees Celsius, I see that the curve that they're talking about here is sodium nitrate, which is this curve right here. And I just want to kind of match things up. So I ride up the 40 because it asked me at 40 degrees. All right, straight up until I hit that line, and this is where it would be saturated, right? Because it's directly on the line. That's the maximum amount we can have, and you kind of just try to eyeball going over, and I don't know, it's about 103 grams, right? And this is going to be multiple choice, so you're going to be able to, pick the closest value to that, right? So that's what we're doing here. And then over here, we have just this saturated, unsaturated, supersaturated, knowing what it is for each of these. So remember, unsaturated means more solute is able to be dissolved. Saturated is the maximum amount of solute has been dissolved, and supersaturated is more than the max of solute. Actually, let me reword that because that's going to get a little funky. More than the max and is unable to all dissolve, right? So there's some left over is what that supersaturated means. So it's like more than the maximum amount able to dissolve. But it asks, okay, if we have 85 grams of that sodium nitrate that we were just looking at 60 degrees, are we saturated, supersaturated, or unsaturated? Remember, above the line is super, right? On the line is saturated. And then below the line, any of those lines, is unsaturated. So at 60 degrees, I match up 60 with 85. Whoa, that deviated right off that path, huh? So we go. This is, I believe, 80 to 85. And we see here's where we are in terms of how much we have dissolved. And this is our line. It's well under it. So that's why we know that that would be unsaturated. This is unsaturated there. All right, so our equations for this unit, the first of which was our molarity equation. So we have the M equals N over V, where N represents moles, V represents volume, and of course this has to be in liters, and then M is the molarity or the concentration of our substances. So looking at that, we can just kind of use the equation to help us out. But M and V, I'm looking for N, which is moles. V is 350 milliliters. But remember, 350 milliliters, there are 1,000 milliliters in every liter. We have to convert that, and that gives us 0.35 liters. So you can just move the decimal back 3 times. So we have 0.35 liters, and we have a 0.5 molar solution, a concentration of 0.5. So here's our equation. We have N over V. You plug in what you know. That's 0.5 equals N over 0.350. And you multiply both sides by 0.350. And you end up with I believe 0.175 moles. All right. And then over here, well, let's try to see what we're looking for and what we're given. In this case, I give you the volume. It's 2.5 liters. We don't have to do anything with that. I'm asking for molarity, so I don't know that. And I give you grams, but the unit for what we need it in is moles, right? So you guessed it, you're going to have to find the molar mass of sodium hydroxide, which is 40 grams per mole, and we're going to have to use that to then convert 125 grams of sodium hydroxide to however many moles of sodium hydroxide that would be equal to. So doing a quick stoichiometric, well, not really stoichiometry, but a little quick unit conversion here. I think always dimensional analysis is stoich, but it's not necessarily. Grams go away, and then we end up with, I believe, 3.125 moles of sodium hydroxide. So 3.125 is the value that we're going to be using in this equation, and moles is 3.125, 2.5 there, and our answer ends up being 1.25 molar, big M for molarity. The other equation that we had in this unit for solutions, aside from the molarity equation, was our dilution equation. Oh boy, I apologize for that. Can't do much about that, and I can't pause this. So, and you've met the dogs. M1 times V1 equals M2 times V2. In terms of our equation, in this case, when we're talking about the dilution equation, you do not have to change the unit for volume from milliliters to liters. And the reason being is because it's a ratio anyway. So anytime you have the same variable show up on both sides of the equation, like volume does here, you don't have to worry about what unit that volume is in. All right, so you're going to see me just use milliliters. And so you could change it to liters if you want, if you're comfortable with that, but it is completely up to you. So I like kind of just labeling, again, what I know and what I don't. All right. 15 molar. How do I know that's molarity 1 or the first concentration? Oh, that's because that is what I currently have. And because it's telling me that it's being diluted, that means that that's what I had started with, right? And this is the value or the amount that I had started of that. So those are context clues. It's not always M1 and V1 because they came first, right? And realistically, it doesn't matter. But that's kind of how you should go about that. Like, look for those keywords like diluted or changes or evaporate. Like, those are the keywords that help you differentiate between what's M1 and what's M2, what's V1, what's V2. It's asking me what the new concentration, that's another keyword to know that I'm looking for M2 there. And then, of course, after the dilution, I have 850 milliliters. And our equation, of course, is above, so I won't write it again. I was about to. But we just plug in what we know, right? 15, we know 50. We know that we don't know M2. And then we have 850 that we know. Say you simplify, you get, I believe, 750 on this side. And we're going to divide both sides by 850 to get rid of it on that side, get the variable by itself, and M2 is going to be equal to, I believe, 0.88 molar. So our answer is 0.88 molar. Now, again, does this make sense? Well, when you dilute something, you make it, or you should be making it, less concentrated because the volume goes up, right? And that's the whole idea. That M1 and V1, for the most part, have a higher concentration because there's a lower volume, right? And to dilute it, like when you dilute something, you actually increase the volume there in order to decrease the concentration. So that's the goal there. So we see that relationship holds true is when I increase the volume and I increase it by 800 milliliters, it's a lot, and it decreased my concentration by a good amount as well. The three primary ways, one is change, dissolve faster, and I'm going to do specifics. So you could raise the temperature, right? You can do what we call agitation, which is just stirring. And then, of course, you can increase the surface area, or what we do is say crush to smaller pieces. And of course, that's why a lot of our sugar packets and things that we have to dissolve things or to dissolve, those come in those very, very tiny granules as opposed to big tablets. Describe how the solubility of a solid changes with temperature. And the solubility, basically, as temp goes up, more solid is able to be dissolved in the same amount of solvent. And remember, solute is what we're dissolving. Solvent is what does the dissolving most often than not. That's going to be that 100 grams or 100 milliliters of water. And then just to kind of show you, right, if I have whatever the grams is per 100 grams of water, like we have on our curve above, and temperature is on here, the higher the temperature gets, you see all those solids have a trend upward, right? That means we can dissolve more of it. And then, of course, gas is actually the exact opposite. So as temp goes up, we say less gas is able to stay dissolved in the same amount of solvent. Ooh. And the example that I like to use, the example for how this looks in real life is soda or pop, right? Whatever you want to call it, soda pop goes flat when warm. Right, and that's the idea behind this. So the if I wanted a visual representation, right, the amount in grams that can dissolve in 100 grams of water as temperature goes up is actually opposite now, inverse, right? We can only dissolve, we dissolve better when we're cold compared to hot, right? And it's kind of the rationale behind that. So there's our solutions portion. All right, only a couple more to go.